So actually, this is a little bit of, oh, no, this is CH2. Well, actually, this is a wash. So, but anyway, you get the idea here. This is more oxidized, right? Yeah. So as you oxidize this, these are the stair steps I was talking about. Each time you oxidize a molecule, a little bit of energy gets released in our stair step. And so we're collecting that energy as ATP and collecting energy as NADH as well. How are we doing?
Just to kind of go back to what you said way earlier. So the two molecules of pyruvate, they begin the steps of the Krebs cycle.
So we're going to take pyruvate and we're going to move it into the Krebs cycle. Pyruvate ends glycolysis. It doesn't start the Krebs cycle. There's a step in between. So, all right, more questions? How are we doing in the back there? Feeling good? Nods are good, or tell me, or ask questions. I want to make sure that no one's lost. Yes?
So when you said it gave phosphates, at which stages when the glucose goes in, when does it give all those phosphates?
So it doesn't give any phosphates, but you use ATP here, and then you get HEP here. So the phosphate is always, in the case of when it's, so this is the high energy molecule. So you put energy in here, and you get energy out here. And the energy is in the form of ATP. ATP has phosphate on it, part of the molecule. Other questions? Okay, are you ready to move on to the next step? No? Nobody's like, I'm just not going to answer that question. All right, let's do a study guide question. We talked about this. In the first step of glycolysis, the cell spends an ATP and phosphorylates glucose as soon as it enters the cell. Why does the cell do this? Give 2 reasons. And I gave you 3, right? Yes. So we'll do 3 on a test. I'd only ask you to do 2. All right, who wants to give me the first reason?
It causes a concentration gradient.
It forces there to always be a concentration gradient. Correct.
It locks the glucose in there.
It locks the glucose into the cell permanently. Okay.
So then the glucose is destabilized and it starts to break down.
That's exactly right. So then we got our 3, right? It destabilizes the glucose molecule, it makes it more reactive, and more able to participate in the steps to break it down. So those are our 3 reasons that I'm looking for in that question. All right. And the answer to that question is actually on that slide, right? So if you, just to kind of point this out, because I think sometimes it's hard to realize that the answers are here. So the answer to this question is on this slide. There's the 3 reasons, right? Does everybody see that? Okay. So you've got the answers to that. Okay. All right. So glycolysis is the first step, and we've taken our glucose molecule and we have partially oxidized it to pyruvate and chopped it in half. All right, but we still have 2, at the end of glycolysis, we still have these 2 pyruvate molecules. And the next step is for pyruvate to be converted to a molecule called acetyl-CoA. So here's our pyruvic acid, and each one of these blue balls is a carbon. So we're counting carbons. And notice what happens to pyruvic acid. Notice that as we go 3 carbons here, and now what does acetyl-CoA have? It has, so we're losing a carbon, and we're losing that carbon as CO2. All right, so we're losing a carbon as CO2. Another molecule of NAD is becoming NADH. So this molecule, if this molecule, is it being reduced or oxidized? NAD plus is gaining a hydrogen, which means in biology it's gaining electrons, right? So it's being reduced, which means that pyruvic acid must be oxidized. If NAD plus is being reduced, then the pyruvic acid must be oxidized. Do oxidized molecules have more energy or reduced molecules? Reduced molecules have more energy. So our pyruvic acid is basically giving some of its energy to NAD+, and now NADH has that energy And the acetyl-CoA is a slightly lower energy molecule because it's been oxidized. Yeah.
So just want to clarify that pyruvic acid and pyruvate are totally interchangeable.
They're exactly the same thing. They're just the carboxylic acid or the salt of the same carboxylic acid.
Pyruvate and water.
All right. I hear some muttering.
Pyruvate and water interchangeable?
Pyruvate and pyruvic acid are the same molecule. The one is the carboxylic acid and one is the salt of the carboxylic acid. All right. So pyruvic acid has more energy than acetyl-CoA, and NAD plus has less energy than NADH. And we've oxidized pyruvate to acetyl-CoA, and we've reduced NAD plus. This is now a high energy molecule. In the process, we've lost a CO2. And one thing that we haven't talked about that is worth mentioning is the whole chemical equation for glycolysis, right? Do you remember this? C6H12O6, right? Plus 6O2 goes to form H2O plus, right? I think it's 6H2O. So we have, here's our 6 carbons and here's our 6 carbons. Right? So this is what I really want you to focus on here. Is these 6 carbons in glucose are ultimately going to all be part of CO2. What do you think? So what we're doing right now is we're losing our first CO2 in this step. I call this step the bridge step because this is the end of glycolysis, but this is the beginning of the Krebs. So this is a reaction that has to happen in the middle. But you see that we're losing a carbon here. This is the first CO2 that we lose. So after this step, after both pyruvic acid have become acetyl-CoA, how many of glucose's 6 carbons are now CO2? 2, right? Because you had 2 of these for every glucose, which means you're going to make 2 CO2s in this step for every glucose molecule. All right, so we have, in our chemical reaction for glucose, we have now 2 of these CO2s have been formed as we break down the molecule. All right, so acetyl-CoA is what enters the Krebs cycle, not pyruvic acid. Pyruvic acid is the end of glycolysis. All right, so what I'm going to do now is we're going to switch slide sets to microbial metabolism 2. How are you doing brain energy-wise? How about we'll go through the Krebs cycle one time, and then we'll do cholera. And then we'll come back on next Tuesday, and we'll go through the Krebs cycle again. What do you think? Yeah? Okay, so that way we do it twice. I can see some exhaustion, but at the same time, I think repetition is worth it. So, okay, let's do a few clickers here. Let's see. I'll get the clicker thing going. And then we're going to go through that. And this. Okay. Which of the following is not produced during glycolysis? All right. Last chance to click in. All right. Almost all of you correctly saying glucose is not produced. ATP is produced, NADH is produced, and pyruvate is the end product. Okay? Glucose is not produced. It's used up, but it's not produced. NADH, is this the oxidized form of the molecule or the reduced form of the molecule? NAD plus is the oxidized form. So you'll kind of want, if you miss this, you're going to want to know that, right? If it's got the hydrogen, it's reduced. And if NAD plus, it's the oxidized form. All right, at the end of glycolysis, how many carbons have been oxidized all the way to CO2 from one glucose? All right, at the end of glycolysis, how many carbons have been oxidized all the way to CO2? Yes.
Counting the bridge step?
Counting the bridge step.
Counting.
Not counting the bridge step. At the end of glycolysis,
Okay.
not counting the bridge step. Yes, confer if you need to. This is not, the end of glycolysis is pyruvate, right? The end of glycolysis is pyruvate. Did you guys have a chance to change your answer? All right, let's see what you guys said. Oh. All right. We're going to do this again. So I want you to talk in a little group. You got 1 minute. Revise your answer and we'll do it again. Let's test this. It didn't work well the first time, but I'll give it another try.
I put 0.
Work on it.
Well, I'm also looking at it here. There's 6.
She said not including
There was no hardness, but now I'm looking at it. The ones that are oxidized are these two. They lost 2 hydrogens. So, are probably right. I feel like it's 2 now that you're saying it, because then these 2 lost hydrogens, so they're oxidized. Yeah, originally I put 2 and 0. I'm gonna put 2 and 1.
Okay, so give this diagram.
All right, I've reset it, so go ahead and now that you've conferred, I want you to re-answer the question and see if you would do better. I read about it. It's a technique. It's a technique. It's a thing. It's a different word. You have to talk to each other. The first time you did it, you didn't know. Oh. You didn't do that. All right, you guys all click back in? No, there's like 7 people missing. Okay, 3. All right, let's see how you did the second time. Oh, nice job. Okay, I would have liked to see 90%, but that's way better, right? At the end of glycolysis, what's the ending molecule of glycolysis? And pyruvate has how many carbons? 3. And how many pyruvates do we have?
2.
And so that's a total of how many carbons?
6.
And how many carbons does glucose have?
6.
So we haven't lost any carbons yet, right? Yeah? Okay. All right. So did that help having the top? So that's how it works better, right? I think it's going to take me some time to figure out when it's the right technique and when it's not. Okay, so there's our summary of glycolysis stuff. Here's one more clicker question. Just to make sure terminology is good. When oxygen is present, the system is aerobic or anaerobic? All right. This seems like a too easy of a question by how fast you're answering it. Let's see what you guys said. Oh, you have to say it again. Because I hit the wrong button. All right, We're going to get rid of that question. All right, monoxamine present things are aerobic, that's exactly right. Okay, so in an aerobic system, we said that pyruvate is going to be converted to acetyl-CoA. So here's our pyruvate. We have not lost any CO2 yet. But we said that it's going to get converted to acetyl-CoA, and we said it gets oxidized or reduced. It's oxidized, right? And NAD plus is oxidized or reduced? It's reduced. So which molecule has the energy now? NADH does, right? Well, we've lost a carbon and CO2 for every pyruvate. So acetyl-CoA is the beginning of the Krebs cycle. And so we're going to go through the Krebs cycle once. If we have time, we'll do cholera, otherwise we'll save it. But I want to be able to do it twice on 2 different days for you. In prokaryotes, the Krebs cycle looks a little different than eukaryotes. And I want to bring you back to our conversation of endosymbiotic theory, where we said that the big cells engulfed the little cells, and the little cells became the chloroplasts and the mitochondria. Remember, we also said that mitochondria are the powerhouses of the cell. So they are the structures in a eukaryotic cell that make all of the ATP. All right? In a bacteria, all of that has to be done in the plasma membrane of the bacteria. But in your cells, it happens in the mitochondria. So the mitochondria, in a eukaryotic cell, acetyl-CoA is actually produced in the cytoplasm of the cell, and then it gets shuttled into the mitochondria. In our bacteria, in our prokaryotic cells, the Krebs cycle just continues in the cytoplasm of the cell, and the bacterial cell membrane itself performs the functions of what the mitochondria would do. And of course, all of that makes really good sense when you relate it back to endosymbiotic theory, knowing that these little bacterial cells became what are now mitochondria. It's all interconnected. All right. So here's our overview of the Krebs cycle. And we're going to do this twice, once today and then once again on Tuesday, right? So this is our first sort of rough sketch through the process. All right, here's our pyruvate again. This is the end of glycolysis. And we haven't started the Krebs cycle yet. We're going to lose the CO2. We're going to oxidize pyruvate to acetyl-CoA, and we're going to create a high-energy NADH molecule. NAD plus is reduced to make a high-energy NADH. Acetyl-CoA is what enters the Krebs cycle. And so I want you to notice it's a cycle, right? And we actually start with a 4-carbon molecule called oxaloacetate, and it is going to combine with 2 carbons of acetyl-CoA to form a 6-carbon molecule named citrate. Now you can memorize all these intermediates. I actually don't think it helps you understand the Krebs cycle. But here's sort of the big picture. The 6-carbon citrate gets isomerized to isocitrate, and then we go through another big step. We're going to lose another carbon in CO2, and we're going to make another high-energy NADH. So we know that isocitrate must be oxidized or reduced in this step. Isocitrate must be oxidized or reduced. Okay, let's do NAD+. NAD+ is in the same reaction. Is this molecule being oxidized or reduced? So if this is reduced, then this one must be oxidized, right? And when we oxidize molecules, we're pulling energy out of them, and we're putting that energy here, right, on NADH, and we're going to save it for the electron transport chain. All right, we lose the CO2. At this stage, how many CO2s from one glucose molecule have been lost? I hear people saying 4, right? Because for every glucose, how many times do we go through Krebs? Because we have 2 pyruvates for every glucose, which means that we have to go through Krebs cycle 2 times for every glucose. So every time you see a CO2 loss here, it really means we're losing 2 per glucose molecule. Everything you see here that happens twice for every glucose molecule. So for every glucose, we make 2 NADH in this step, and we make 2 CO2. In the next step, we're going to oxidize this molecule further. So alpha-ketoglutarate gets oxidized to succinyl-CoA. And we know this is oxidized because here's NAD plus being it's being reduced. So if NAD plus is being reduced, then that means this must be oxidized. Okay? The electrons can't evaporate into thin air, they have to go somewhere. If one molecule loses electrons, another molecule has to gain them. So if NAD plus is oxidized, then alpha-ketoglutarate has to be reduced. And look at this, we're losing another CO2. Okay, glucose had 6 carbons. We lost 2 carbons here. We lost 2 carbons here. How many carbons did we lose here? How many carbons are gone? All of them. So at this step of the Krebs cycle, all of the carbon in glucose has been oxidized to CO2. Remember our chemical equation? Right? That's all 6 CO2. All right, have been lost. But we're not done getting energy out of glucose because we've made a lot of these intermediate molecules that still have energy. So succinyl-CoA now gets converted to succinate. Notice that an ATP gets produced here. For every glucose, how many ATP is that? 2, right? Because we do this twice for every glucose. So this 1 ATP is really 2 per glucose. And we're going to go from succinate to fumarate, and we're going to make another high energy intermediate. FAD, is this being oxidized or reduced? And you know it's being reduced because it's got more hydrogens, right? So this molecule's, this has some energy has been captured here. Fumarate becomes malate. Malate becomes oxaloacetate. Is malate oxidized or reduced? And you know it's being oxidized because this molecule is?
Reduced.
Okay. And so now, oh wait, we've got oxaloacetate again. We're right back where we started, right? And now we have oxaloacetate regenerated so it can react with another molecule of acetyl-CoA and go through the cycle again. So in the Krebs cycle, we burnt out, we had lost 2 of our 6 carbons of CO2. We lose the other 4 in the Krebs cycle. For every turn of the Krebs cycle, we make 3 NADHs, an FADH2, and an ATP. But we do it twice for glucose, so we actually make 6 NADHs for every glucose. We make 2 ATPs and 2 FADH2s for every glucose molecule. Right? So, this is one of those things that seems really straightforward to me because I've studied it and taught it a lot of times, but you might feel a little lost right now.
A little?
No hecklers. But I would really encourage you, we're going to go over it again on Thursday. One of the things that I learned, I still learn all the time, because I'm always a student learning new things, right? Is that the first time I learn a new concept, it doesn't gel. But if I study it again, it starts to gel. And then if I go over it a few more times, it really starts to stick. What you could do over the weekend to make Tuesday really productive is on a blank sheet of paper, try to draw yourself a Krebs cycle and say how many CO2, you don't have to know where they got lost, but how many CO2 get produced? How many times do you go through it for every glucose? What molecules are the starting materials and what molecules are the ending materials? How many NADH, how many FADH2? See if you can do it on a blank sheet of paper. And I think if you do this, don't just